today. I want to show you something else. You can easily take this thing here and you can find out what the sample is by taking this 0 to 2 pi. So what happens is go from -pi to pi of x omega e j omega and e omega. Okay, so you see that this operation is something more general than this, right? Before you have those kind of discrete sample, now I have all omega I can integrate. Okay. So we have this fab transformations, take the signal, go to discrete Fourier transform, and I can go back. And there's a whole story of connecting that. And I want to talk about this in the context of sampling later. But now, what if this thing here has a nice property? And so does all of the Fourier transform. Now, if I go back to the early 60s, remember early on. If I have this now. Now, let's say, very important now. Let S be an LDR system. Let S be an LDR system, right? The system that's linear and time invariant. We know before. Now, if I have an LDR system, what do you remember from the first lecture? What do I have? How can I describe the system? I use impulse response, right? I use impulse response, so then I have the system that have H and here is impulse response of the system. Okay. So on this formula, what you need to see now is I'm going to take each of these components as one basic signal. The signal that is E j omega n. The signal E j omega n. So that means the signal is at the eastern end, we have E j omega n. Okay. If I take that signal as input, okay, then the output of these systems, to be more precise, maybe we can know a particular frequency. So I fix this omega naught. Okay, I fix that signal here, and I want to work out what would be the output. What would be the output of this? So I take that thing here and I take the output here. Then the Y. So the output of that particular systems, is, I can write them now, the output that Y and here, simply just taking this and converting this. Right? Taking this and converting this. And write that, so summation now, and I take in K, and I take the convolution in xk, and I call this thing here, so this is xn. Xn equal to this. Taking this convolution here, I have h of n minus k. Okay? So I'm taking that signal there, and my output of this signal, my output signal, simply now, I can write this now equal to summation. So I plug this guy inside. What is the easier way to show? Taking this, so the convolution maybe I can write, easy to show that I can swap these two things, right? If I change that, the convolution maybe I can write, it is hk and it is x n minus k. Very easier. Okay. And if I have this now, then I have summation in k of hk, and now I replace this xn minus k. So what is xn minus k now? It is ej omega naught, and I have outside that replace n by n minus k. Right? N minus k. So I have a summation, and sum in k, summation in k. So this omega n here doesn't matter. When you go inside, move them outside. So it equals ej omega naught n, and inside I have a summation in k of hk, ej minus now omega naught k. Is it correct? So what is this thing here? What is this thing inside here? By definition, it looks like this thing here. Right? So now it is equal to ej omega naught n and then h of omega naught. Okay. So now you recognize the body. This omega naught is something I fixed. I fixed this. I fixed this thing here and have a signal of that particular frequency omega naught. I pass it through the systems. I get out something like this signal with that particular frequency. Only thing I change is this. This thing I now get scaled up. Right? Can you see that? Simple information there. The bottom line here is something we can go here, this thing here. We can go to this eigen signal. Right? The concept like the eigenvector. Remember, like you have an eigenvector, go through a matrix, you got something scaled by the eigenvector. So this is an eigen signal. So this component here is an eigen signal of any LTI system. So take the signal. So now you go back to this formula. You have a signal, and because now the signal is infinitely long, so my summation now is 34 integral, loosely speaking. And I have all of this x omega, and tell me now for each particular omega, this is a one particular signal, and that's the weight, right? And all the weight here. So I have a signal, I can expand them to Fourier basis, right? Different components. And I take those components with the divine contour. I break the signal into those components and put the signal through the system. It's like putting each component through the system. Each component, when they go through the system, remains the same, right? You're exactly the same, except it gets scaled by this number, right? So you can see that this h omega is very important because the bigger h omega telling me that that particular frequency when it passes through get amplified. The smaller h omega, that means that particular frequency go through get killed, get rejected. And that is really the concept of filtering, right? You let an LTI system filter out any particular frequency or get particular frequency go through. Right? So you see that really the viewpoint taking the signal and break them into